Hello everyone, I am Jinghan Hu from Arizona State University. Today I will be presenting our work, Sensor Realistic Synthetic Data Engine for Multi-Frame High Dynamic Range Photography, in collaboration with Qiumin Zhou, Zishan Nadir, Sokjong Li, Hamid Sheikh, Yongjong Yu, and Michael Poley from Samsung Research America, and Osama Nabil from UCLA. AI camera has become the key enabler of a new level of camera usability and image quality, and the recent progress of mobile application processor has made AI camera practical for smartphones for daily usage. However, good datasets are often missing for training AI camera, which is critical to AI camera performance. In particular, for AI HDR imaging, the deficiency is not only limited to a small amount of training and testing data, but also limited ranges of motions and lighting changes, etc. in the scene. And simple models often used for generating ground truth. They all lead to worse AI camera performance than expected. Our contribution in this paper is a systematic sensor-realistic synthetic data engine to convert game engine-generated raw synthetic data into sensor-realistic synthetic data with sensor characteristics modeled for specific devices applied, such as noise and color gamut. As a result, unlimited amounts of training data can be unlocked. We further validated our sensor-realistic synthetic data engine in the context of AI HDR imaging on real captures from a Samsung Galaxy S10 Plus mobile device. HDR photography merges multiple low dynamic range images captured consecutively at different exposure levels to reproduce an image with high dynamic range of luminosity. It is one of the essential camera applications that users use every day. In this example from Wikipedia, we see great performance improvement comparing non-HDR with HDR images. However, because of this merging, multi-frame HDR suffers from corner cases and artifacts from dynamic scenes. Recent years, researchers proposed several deep learning-based approaches to overcome those limitations. For example, deep high dynamic range imaging of dynamic scenes introduced by Calentry proposed to learn the merging process. End-to-end deep HDR imaging with large foreground motions introduced by Shangzhe Wu proposed to learn the mapping between LDR and HDR images directly without optical flow alignment. Unfortunately, prior works do not perform well on real mobile devices in various real scenarios. A core reason is that both prior work only compiled and used a small training dataset, the Calentry dataset, which only consists of 75 sets of images. It is well known that capturing real data is expensive. Are there any alternatives? Can we use synthetic data, which is really popular in recent years, especially when synthetic data has so many advantages, such as achieved at large scale, privacy preserved, and easier for generating a ground truth in many cases? The answer is yes, we absolutely can use synthetic data, but not with the gap between real and synthetic data unfilled. Images generated from the game engine are realistic but raw, as they are always in the same color space and do not have any noise. However, real images can reflect various color spaces and noise characteristics of different image sensors. Directly learning from raw synthetic data makes AI networks more susceptible to noise and thus perform even worse in the final HDR output. To address this, our solution is a sensor-realistic synthetic data engine, which is a systematic pipeline to bridge the gap between the game engine-generated raw synthetic data and real data in 3 steps. First, we generate raw synthetic data from the game engine. Second, we calibrate the color space of the image sensor and apply it to synthetic data. Third, we model the noise of the image sensor and apply it to synthetic data such that raw synthetic data is converted to sensor-realistic synthetic data that can be used for training. In the first step, generate raw synthetic data, we rely on game engines such as Unreal Engine for realistic synthetic scenes and human models with various motions. There are other platforms such as Unity can be used. Inside the game engine, we implemented a loop to capture synthetic images. We first moved the virtual camera to a desired location. Then we stopped the subject motion adjusts exposure, and then captures images for static scenes. After that, we resume the motions, adjust exposures again, and then capture images for dynamic scenes. Capturing in-game engine has lots of advantages, including precise control of camera position and viewpoint for under and overexposed regions, precise control of the subject motion for generating ground truth, and flexible environmental control and camera parameter control. Here are two examples of the raw synthetic data captured at 3 exposure levels. In the first row, the robot is waving a hand on the statue. In the second row, the robot is walking in front of a window. There are 3 more examples of the raw synthetic data captured at 2 exposure levels. In these examples, we have more realistic human models, and we use them to simulate small motions that could happen during consecutive captures. For the second step, color calibration, we first put a light probe, which is a stainless steel gazing ball, in the middle of the targeted scene. We capture 2 images using our targeted mobile device to gather all lighting information in 360 degrees. Then we encode the lighting information using HDR shot and import the lighting into Unreal Engine to light up the synthetic color checker. We further adjust the virtual camera parameters based on real camera parameters to capture the synthetic color checker. Finally, we capture a real color checker using the model device and compare it against the synthetic color checker to acquire the transition matrix T. For noise modeling, we model sensor noise characteristics using normal approximation to Poisson Gaussian noise. For each capture condition, we acquire a bunch of frames and time average them to get a noise-free image after excluding defective and saturated pixels. Then we estimate the parameters A and B of a signal-dependent additive Gaussian noise with the following distribution, where sigma ij squared is the pixel-dependent variance. The parameter A and B control the amount of signal-dependent and signal-independent components of noise. Here's an example comparing raw synthetic data against the sensor-realistic synthetic data. After color calibration and noise modeling applied, the sensor-realistic synthetic data shows warmer color and real noise, similar to real captures from a Samsung Galaxy S10 Plus device. We validated our sensor-realistic synthetic data in 2 AI HDR networks. Network 1 is implemented by ourselves, which has the bandwidth map as the AI component, similar to the concept of learning to merge. Network 2 is referred to Wu's work at CVPR, which directly learns the mapping between LDR and HDR images. This work is trained on dynamic scenes, however, we focus on the utility of sensor-realistic synthetic data in static scenes. This table shows the datasets used in each network. Network 1 is pre-trained on real data captured by S10 Plus. Network 2 is pre-trained on real data captured by Canon camera. Then we fine-tune Network 1 and Network 2 with 150 sets of sensor-realistic synthetic data captured with different combinations of exposure levels depending on the network architecture. Ground truth in Network 1 is generated using a proprietary algorithm. Ground truth in Network 2 is generated using the same linear triangular method used in Wu's paper. We test both networks on real images captured by S10 Plus device. Results show that Network 1, fine-tuned with sensor-realistic data, has higher PSNR and SNM value in both tone-mapped and linear domain. Specifically, in this example, the ground between legs show more details. Note that this network does not improve that much because it is already trained on real data captured by the same model device. Results for Network 2 show that Network 2, fine-tuned with sensor-realistic synthetic data, also has higher PSNR and SSIM value. The example output from the network fine-tuned with sensor-realistic synthetic data perform very close to the ground truth, in which we can clearly see even in the dark. Note that this network is pre-trained on the Calendar dataset, which contains real data captured by a Canon device. We further studied how different color spaces and noise characteristics applied to synthetic data can affect the final HDR performance, such as applying a different color space modeled for an S9 device. And we find that applying the correct tensor realism to the synthetic data is necessary to yield the best HDR result. Thanks for hearing, and I will be happy to take any questions.